Okay, so today we look at what happens if you take different parameterizations of a curve. For instance, let's take a unit speed parameterization. Say, call this gamma from say, or you take alpha bar, gamma bar from alpha bar, beta bar to Rn, and another is a unit speed parameterization. You take another reparameterization, which is also unit speed from alpha cap beta cap to Rn. So there is a function from here. So let's call this u the variable here, and the variable will be here. So there is a function. So v is a function of u. I use the function here. Function name you could have given some other, but I will use the function name also v. So the every element here is vu. Okay. So you have the diagram is like this. This is gamma bar. This is gamma cap. And so if you look at this, your gamma cap composite v, this function is the same as gamma bar. Both are unit speed parameterizations. This is of course at the point. Okay? So let's see what happens to. We are interested in finding out what is this function going to be. Okay, so let us differentiate. So this is gamma cap. So gamma cap, the variable here is v. So d by dv of gamma cap. So norm of this, of course, at the point v or vu, whatever you like. Okay, this is 1 because it's a unit speed parameterization. This is going to be 1, and this is going to be d by dv of gamma hat composite v at u. That's what it is. That is equal to, now look at this. This is d by dv. This gamma hat composite v is gamma bar. D by dv of gamma bar at u. So let us do this. This is actually d by du of gamma bar at u into du by dv. Okay, so that is equal to, this is a real valued function, this is a vector valued function. So this is norm of d by du at gamma bar at u into modulus of du by dv. Okay. Now this is 1 because gamma bar is also unit speed. So therefore this is going to be du modulus of du by dv. Okay. So now you can easily see, therefore there is what du by dv is actually equal to 1. So this we have seen, but now I am telling you, any two unit speed parameterization, we assume one is the reparameterization of the other, then they are related like this. So therefore your u, so this du by dv is equal to, I call it epsilon, where as we have seen earlier, this is a connected set. So therefore the derivative is a dv by du is a derivative of the function v. therefore the image has to be connected, and hence you cannot take value of 1 and minus 1, so it has to be always equal to either 1 or minus 1. So where epsilon is equal to 1, or you can say epsilon is in this set, minus 1 or 1. One of them you can take. Okay? Alright, if we have understood this, so therefore u is equal to epsilon b plus some constant. This epsilon is either plus 1, that means, so either u is equal to v plus c for every. So this is actually, I should say u is a function of v, will be that. Okay, so I finally landed up v as a function of u. I was thinking of, anyway, it's a bijection, so it doesn't matter being a reparameterization. I wrote, okay, so I should have come the other way, then I would have got dv by dv. So epsilon times v, so this is a function of v, and or u is equal to minus v plus c. So in particular, if you look at this, these two intervals are also related like that, because this is a bijection, your v is a bijection, u is its inverse, that's also bijection, and they are related like this. So now, so let us look at the second derivative. So forget about this. So d square gamma cap by dv square at the point d. Okay. So this is d by dv of dv by, sorry, d gamma bar by dv at this point. That's equal to d by du of, we have already computed that, d by du of d gamma bar, this is the one, d gamma bar by du, d gamma bar at du by du times du by dv at the point B. And this is epsilon. So that is equal to epsilon times d by du of d by, this is v, sorry, this is v by dv, this is d by dv, d by dv of d gamma bar by du and du into, that's all. Okay. So let's write, this is equal to epsilon d by dv. Yeah, this is something. Okay, let's look at this. This is gamma bar. So gamma cap composite B is gamma bar. So this is gamma bar at u. So this is gamma bar at u. You can see that gamma bar is conducted at u. Okay, so this is d by dv of gamma bar. So this is this. Let's write it again, by du at u into yeah. So this is what we are looking for. So that is equal to epsilon times d by du of d gamma bar du at u into du d by dv is d by du and du by dv, and that's again at some point v. This is uv if you like to write. So that is again epsilon. So epsilon square d square gamma bar by du square and u your uv. So this, now you can see this epsilon is either 1 or minus 1. So epsilon square is always going to be 1. So this is equal to d square gamma by du square. So d square gamma by gamma, yes, d square gamma cap at vu and v is the same as d gamma at du at v. So the two are actually same. D square gamma cap at v, yeah. You can tell.
Bar. Bar, gamma bar.
Ah, yes, this is gamma bar. So the respective points, the second derivatives are same. Though the first derivative, the sign may differ depending on your epsilon. But this doesn't depend on epsilon. So your second derivative is the same as the for both the parameterization. So that is what the point at which you evaluate. I mean, if it is v here, then this is uv here. If you take u here, then it will be vu here. That's all. It's the same. It's the same respective points here. That's all. Okay. Yeah. So this is important for the curve because let me tell you what does it mean. Suppose your parameterization is in this direction, your u is in this direction, then the tangent vector will be like this. If your v is minus of that, then your v will be on this direction and the tangent vector will be in this direction, unit vector both. So your gamma, suppose gamma bar is in this direction and gamma cap is in the other direction, then the tangent vectors get reversed. But the normal does not get reversed. Normal is always going to be, from both of them, you get the same gamma cap, second derivative. D square gamma by d, gamma cap dv square. And that's the same as d square gamma bar by dv square. Whereas this is your gamma bar. So d gamma bar by du, and this is d gamma cap by dv. They are in opposite direction while the second derivative will be in the same direction. So that's a very important thing. It's independent of parameterization, unit speed parameterization. Both of them give the same vector. Notice that this also says that the curvature that we defined as the norm of the, if you start with any unit speed parameterization, then the curvature is defined as the norm of the second derivative, d square gamma bar by d u square. So if you take gamma cap, another unit speed parameterization, you will get the same curvature. But the signed curvature is slightly different. What is the signed curvature? Since the second derivative is the same, the d square gamma bar by du square is the same as d square gamma cap by dv square. That we have seen. But for signed curvature, let's look at this picture that tells you everything. So what you do is, this is your tangent. assume that this is a plane curve and you look at gamma bar, so it moves like this. Then the tangent vector you rotate, tangent vector is unit vector because it's a unit speed parameterization. So you rotate this by pi by 2, 90 degrees, pi by 2 angle in the clockwise direction. So this is going to be your ns. In the case of gamma bar, so ns bar. Now, look at the gamma cap. Gamma cap is coming, the tangent vector is in this direction. So if you rotate this by pi by 2 to get your signed normal, so it is going to be, this is going to be your ns cap. So ns bar and ns cap are not same if the parameterizations, the variable has if your epsilon is -1. So therefore, your signed curvature, which you write the second derivative as a multiple of this, and this is a multiple of this. The second derivatives are same, but ns bar is going to be minus of ns. So your ks bar, bar will be accordingly minus of ks cap. Because I can rewrite this, so you will see here ns bar is going to be, first you should understand that gamma bar d gamma bar by du is going to be minus of d gamma cap by dv. So you rotate this by pi by 2 positively and rotate this by pi by 2 positively. So this will give you your signed normal with respect to gamma bar. And this rotating by pi by 2, you will get signed normal with respect to this parameterization. Okay? So now let us look at the signed curvature. The signed curvature is given by, you take d square gamma bar by d, I should be careful, du square. Then this is going to be ks, I keep using this bar for things associated, all the objects associated with the gamma bar. Ks bar, ns bar. Okay? Whereas with respect to gamma cap, what will you get? D square gamma cap by d v square, that is equal to ks cap ns cap. Now you see that these two are equal, whereas this is going to be, this, if you look at your ns cap is going to be ns minus of, ns bar is minus of ns cap. So you can write it as ks bar minus ns cap. I'm sorry, ns cap. But these two are same. Therefore, these two have to be same. Therefore, your ks cap, kappa s cap is the same as. So signed curvature depends on the parameterization. Whereas the general curvature doesn't depend, and you can see that we take the no, so it doesn't matter at all. Otherwise also the second derivative is not dependent on the unit speed parameterization. It is independent of it. It depends on the pointer. So that's what you have to understand. See, given a curve, we know how to compute the signed curvature. Given a parameterized curve, you take a unit speed parameterization, any one you like, and then you know how to compute the signed curvature. So our question is the other way. If the signed curvature is given, can you get the curve back? For every plane curve, you can compute the signed curvature. How far? The signed curvature gives information about it. This is an information about the curve. How far it determines the curve. That means if you are given the sine curvature, can you tell me what is the curve that you are talking? Is it possible? That's the question. Okay. So let's look at suppose the sine curvature. Sine curvature is a function at every point in the domain alpha beta. You will have a number, which you know how we have. We take gamma dot, rotated it by pi by 2, positive anti-clockwise direction, and your second derivative is in that direction, and therefore second derivative is a scalar multiple of the vector that you got, which you call the sine normal, and that scalar is called the sine curvature. Okay, so at every point you are getting that scalar, one real number. So if you are given that's also, we saw that it's also smooth. So this is what we have written: d square gamma by ds square. You can write gamma tilde if you like, at any point s is equal to this number. This is the sine curvature at s into the sine normal. This is obtained by taking this is your tangent, this is your d gamma by ds and gamma s. This is the point gamma s, gamma tilde s, and the tangent vector, and rotated by pi by s. This is what you are going to get your this. Of course, all the points we are saying evaluated at. So this is the interval alpha beta. Here is your s. This is your gamma s. So every information we relate to s. Okay. So suppose one such function is given. So now you can easily check that this sufficient smoothness says your ks can also be written like this: d square gamma by ds square at a point s dot nss. So so these two are smooth functions. If your functions are smooth enough, if gamma dot is smooth enough, then the rotated one, which we know how to write the formula also we know, that's also going to be smooth using just cosine and sine. So that is also smooth. So this is a smooth function. Now, if you are given such a smooth function from alpha, beta to r, these are all real numbers, can you get a curve for which this given function is the curvature? Sine the curvature, of course. So that's the question. So let us start. Let's write down. Let me use a different notation. K from alpha, beta to r. We have no idea what kind of numbers you are going to get. R be a smooth function. Okay. Question is, can we get does there exist a smooth curve unit speed? Exists a unit speed curve gamma from plane curve such that the sine curvature at s is equal to as for every s in alpha. That's the question. So we don't know whether it exists, but of course there is a natural way mathematicians do that. Try to see what happens if there is one, and try to relate it to k whether we can do it. So, and then of course you do the backward. So assume that there is one such. So what does that mean? That means assume there is one. We still don't know whether there is one. Assume that such a gamma exists. Okay? So what does it mean? We have to relate to this. So we have to come to all this. So gamma dot at a point S. So what is given here? Kappa is our K is the curvature is what we have to. So we still write down, we don't know. Then I can write it as d by ds of gamma S. And this is a unit vector because this one is unit speed. So we could probably write as cosine of something and sine of something. Of course, may not be S because it's just a function. So it will be some cosine phi of S, sine phi S. We have already seen this, where phi is a function from S to alpha beta to R. Okay? So such a phi exists because of cosine sine function locally 1 you can invert and you can get such a function because this is a unit vector very. So every point you can write it as, but you can choose your phi in such a way that this becomes smooth. Now if this is true, then we have seen yesterday that earlier that for this curve, the kappa S is equal to d phi by this S. This we have seen. In case there is one such, then for that gamma, this must be the signed curvature. Yes. But then what we want the sound curvature should be Ks. So let us take this to be equal to Ks. So let d phi by ds at S is equal to K at S. Okay? Now we are going to get our phi from here. So that's if K is the different derivative of phi, then what is going to be phi? So let us fix an element here. Let's fix T naught by integrating T naught to alpha beta. This is standard. If you know the derivative of a function, from there you get the function, but for a small irritating factor. So let us fix this and define then your phi is equal to integral from T naught to have to be careful, S phi u du plus a constant. You can see d phi by ds is equal to k. So now you can see that the d phi by ds is actually equal to k at S. This goes. So this up to a constant you can completely determine phi. Okay? So once you have phi, then we are through because now we can easily write. So therefore your gamma dot d gamma by ds, that is your thus. So you can write it as cosine integral from T naught to S or S naught to S, it doesn't matter. Again, I just took it as T naught. Ku du, this you can integrate, you can find out, be careful, plus c, comma, sine, integrate from T0 to S, du du, plus c. Okay?
There is no dot there. Gamma.
Yes. Okay, from that expression we can write your gamma. So your gamma, we have already given what is d by ds of gamma at some point s. So you can take another point s0, fix s0 in alpha beta, and then you write your gamma as gamma at s is equal to integral from s0 to s, whatever that expression there, which is something like cosine of something, and gamma at t, s0 to t, cosine at ds, whatever this expression, until it is t0 to s, k, this is ku, du, ds, and similarly the second expression. So we could plus c, there is a constant here, I'm sorry to say, plus c, then you take ds. Yeah, that's right. So this is a function of s, so you differentiate with respect, integrate with respect to s, and from s0 to t, so that gives you this value, similarly the other. So this gives you gamma. Now you can go back. What is gamma dot? Gamma dot is the expression that we had earlier. So d by dt of gamma at t is going to be, you differentiate the first coordinate, you get cos this expression at the point t, so this is integral from t0 to, this is at the point s, so this is to s, ku du plus c, comma, next one is, the other one will be sine, integral t0 to s, ku du plus c, and thus. Now, so this is your gamma dot. So d square, now we know that this can be written as cosine some function, denoted as phi s, sine, both these are same, sine phi s, okay, where phi s is, I'm just going backward, this is the proof. So you define gamma like this, we invented the proof. Now in a book or in a standard form, you write this expression, take this as gamma. So d by dt of gamma is going to be this expression, where phi s is equal to integral t0 to s ku du plus c. Now let us take d phi by ds. So once you know this phi, we know that the curvature is nothing but d phi by ds, that we have done. So d phi by, so your ks sine the curvature upon s. Sine the curvature for gamma is d phi by ds, and d phi by ds is nothing but ks. So therefore, this is where whatever we have done, proof starts from here. You take 2 points, fix this, and write down this. Okay? Let gamma be this, then the derivative is, the tangent vector is this, and therefore the curvature, sine the curvature of gamma is this, which is equal to you can see if you differentiate this with respect to s, the curvature is, the derivative is k at the point s. So that goes. So there is something more I should tell, because it should be a little more, because when you differentiate, this can go up to any d1. And there is a d2 on here. Here we can take plus d1, a constant, and the other expression plus d2, a constant, and when you differentiate, that will disappear. The d1 will disappear, and you get this. Similarly, so there are two constants involved. One is that constant that we have got, we get here. So here in this integration, you put one more constant, d1 and d2, that you see. Because it's subject to these two constants only, we can get this. That is, yeah. So if you look at it, what are these constants about? Okay, gamma is written as this expression plus a constant d1. So you can write it as gamma t is equal to, that constant could be anything. This expression S0 to t cos something here. Integral t0 to s, that notation I should have written that then. Ku du plus a constant, comma, integral from, sine plus d1, comma, integral from S0 to t sine s ku du plus c. There is a ds here, ds plus du. So if you differentiate, then you get this expression, and the integral goes. So you get d1. These are two constants where you have your d1 and d2. C, d1, d2 are constants, fixed constants. So that's the most general form that we are seeing. So now if you look at this, this is quite interesting. You know, there are two expressions here. So this could be written as cosine of a plus b formula you can apply. So it will be cos of this plus cos c, then minus sine of this sine c. Okay? So it will have a, what about this guy? This guy, sine of a plus b. So sine of this into sine of c, cos of c, plus cos of this into sine of c. So you leave it. So before that, yes, this d1, d2 I can take out. So that is the next step. That is what you should understand. S0 to t cos integral t0 to s ku du plus c, comma, integral S0 to t sine integral t0 to s ku du. K is a given function, so you can easily do the computation, plus c plus this vector d1 d2. Sometimes, you know, here is one vector, you keep adding. This d1 d2 is independent of your s, your t. So sometimes this is this, if you understand, then you just translate by that one vector d1 d2. Okay? So this now this, if you try to understand this, I don't write a full expression, so you can write it. It's very easy to understand that this, what is wherever the sign is not, the variable is not involved, I will take it out. So you are going to get cos C, and the other one is cos C, cos of this, plus minus sin C of this. So I will take sin C. You can see both places you get the same. And then you multiply, you get this. And this side, you get sin into cosine C. So it will again come to the same thing. So the next one will be cos C into this, and this is sin C for the second one. Sin C, because sine of the C into cos, it doesn't make any difference because it is sum. So sin C cos C into these expressions. What are they? So let us write. You have to expand this cos A plus B. So that is how you get cos C into cos of this. So this will be integral from T0 to S cosine integral from T0 to S KUT. What is cosine? The second part is sine. So integral from this is integral from S0 to S. That is it. I'm only expressing this inner part. Okay? Both are integral from S0 to S. So only inner part I am discussing. That will be sine integral from T0 to S KUD. So this is the vector. Plus, of course, you have this vector. I have written column here. So let us check. This will be what is given inside. The integral is outside. So there is a ds. So this will be cos C cosine this minus sin C sin this. That's done. And that one will be sin this into cos C. Oh, I have it in the other way, right? So this is cosine this, and first term, sin C into sine of this integral plus cos C into sine of this. So that both are same, right? Sin C into cosine of this, sin A plus B. So I will take this as your A. So sine of this into cos of this. Sine of it into cos of this. Next one is cos of this into sine of this. So cos of this into sine of this. That is okay. Both are matches. I mean this, because it's plus, it doesn't matter which one you take A and B. So this gives. So now I will tell you what was all this. Integral from S0 to S. This is a rotation, and this is independent of, ultimately I want to say that this has nothing to do with the integration because it's a constant. So you can always take it out. So this is cos C minus sin C, sin C cos C. The C is any constant, it works. There is no. Thus, cosine integral T0 to S KUdu, sine integral T0 to S KUdu, plus this and these d2. Of course, here you need integration. There is no doubt. Integral from S0 to S ds plus dt. You can have written separate together this, or you can write it. This means here integral from S0 to S, integral from S0 to T, and this is T, that's the gamma T ds. That's it. Oh, if I do like that, then I also write ds here. So that expression is a little. Let me rewrite the properly. This is two coordinates. The first one is integral from S1 to T cosine integral to S du, and then this is a function of S, and this is your phi S ds. This is from S1 to T sine integral from T1 to, this is your phi T1 to S ku du, and then plus yes. Listen, I mean this we have constructed this, and we have already verified that this will certainly give you a curve whose curvature is Ks. We have just seen this. But there is also a converse to it, namely, suppose you have a gamma whose curvature is, signed curvature is Ks, then, and its tangents are expressed using some cosines, in the polar coordinates, then the coordinate, the angle function phi, its derivative is Ks. Therefore, if you have any curve that satisfies the condition that its signed curvature is Ks, then d phi by ds has to be Ks. That's what is your signed curvature. If that is the case, then integrating phi, you will get your, integrating k, you are going to get your phi. So the phi will be like this, except that there will be an additive constant. Up to a constant, this is exactly equal to the phi. Then once you know that the phi is the one that describes the angle. So this is actually equal to, this will give you the derivative cos phi s sin phi s. If you know that d gamma by dt is this expression, well, forget about this part, look at this, then your gamma is integral of this with respect to ds with plus a constant. So that's yes. So there is a d2 that we have added. So this is going to be 1. So if gamma has signed curvature Ks, then gamma will be like this with 3 constants involved, C, d1 and d2. All the gamma, any of course unit speed parameterized curve gamma whose signed curvature is Ks, then gamma will have this expression for some constants C, d1 and d2. All the curves come like this. So that's when you just go back. Initially that's what we did, and whatever we arrived, we took that, and then we came back and we have proved that it has. On the other hand, you can also go back and say that if gamma is a unit speed curve with signed curvature, the given function Ks, then phi has to be this, d gamma by dt has to be this, of course, this places constants are involved, and therefore gamma should be like this. Okay. So now, what is this this character? This character is a linear map. Let me call this rho C from a map from R2 to R2. It is what is that? What is that? Given any point x comma y, x comma y. What is that? How is it defined? It is defined here. Cos x minus sin y. You can see cos x, x and y. So cos x minus sin y. And the other one is sin x. Second quantity is sin x plus cos y. And this is exactly, this is nothing but rotation by.
It should be x cos c, no?
Oh, I'm sorry. Yes. Cos.
X cos
I
c.
think x times cos c. X into cos c is the best way of writing. Make it cosine c minus sin c, sin c, cosine c, x, y. So this will be x cos c minus y sin c. This is x sin c plus y cos c. You can also use this very easily using complex polar coordinates. Suppose you write x, this point x as in polar coordinates, let's write r cos theta, r sin theta. Okay, and substitute there. Then what will be this rho c x comma y? Let's write down. So x is r cos theta cos c minus r, y is this sin theta sin c, and this one is x is r cos theta, r cos theta sin c plus r sin theta sin c, and you can check that this is nothing but r, this is cos c plus theta, r sin c plus theta. That means if you draw a picture, this is your x comma y. So that means this is your r and this is your theta. R cos theta, r sin theta. And you apply this map, what you are going to get is modulus is the same, r, and angle is c plus theta. So this same r, and this is c plus. So you rotate, what you have done, given any theta, theta is arbitrary, c is fixed. So what this map does is rotate the plane by an angle c. So that's rho c, the rotation of r2 by an angle. Angle, of course, always angle is written in terms of radians. And c could be positive, negative, 0, anything. So this is this particular map is a rotation. And this one, the last one, that's a translation. So if I choose this curve, so if you look at gamma naught, let me write gamma naught. Gamma naught is one curve which is given like this: s naught to t cosine t naught to s KU DU ds and S0 to T sine T0 to S KU DU ds. And this gamma naught S, first coordinate and second coordinate, this is also a curve such that its sine curvature is curvature of gamma naught. It's a unit speed curve. All these are unit speed curve for any C and D. So in particular this gamma naught is also Ks, and the general gamma, the gamma is here rho C of gamma naught. You can see this expression rho C of gamma naught plus d1 d2. This is generally called a translation. So I have not denoted any notation. So let me give a notation. Translation by d1 d2 of gamma C rho C gamma naught. So where this notation stands for translation by d1 d2. So you have one curve and take any constants d1 d2 c, you will get a rotation followed by a translation. So one you fix gamma naught, from gamma naught you will get every curve whose curvature, sine curvature is Ks by using a rotation followed by translation. So that is the concept. Okay, so let us just write whatever that we have done so far. So what is the statement? Let's write this as a theorem. Let K from alpha beta to R be a smooth function. So that's what is given. So our aim is to, question was, does there exist a curve, unit speed curve, for which K as the signed curvature? So the answer is yes. So if phi s is equal to integral from, let me use the same notation, T0 to S KU du, and gamma naught S is equal to integral from gamma naught T is equal to integral from S0 to T cos phi s ds, integral from S0 to T sin phi s ds, then gamma naught from alpha beta to R2 is the unit speed curve with signed curvature kappa s at s is actually equal to Ks. Now, whether this is the only, answer is no. If gamma is any unit speed beta 2 r2 is any unit speed curve, smooth curve, of course whenever I say curve I assume that curve such that its signed curvature some notation I require ks, maybe I'll write bar, and s is equal to ks with the same signed curvature as gamma naught as we demand, then there exists C, D1, D2 in R, three real numbers, such that your gamma is equal to first a translation by, sorry, not first, O, C, gamma. Write it as composition, rotation by C followed by a translation by vector D1, D2. That's what we have proved. So they are unique only up to that. There always exists, there exists plenty, but they are all going to be nothing but gamma naught first, followed by a rotation, followed by, so it is like this. So I'll tell you the picture like this. See, you will have this is your gamma naught. Now you rotate it, you make it like this, the curve. Okay, you can rotate it, you can rotate it, you make it like this, then you translate it, you get this. So there are plenty of curves of this type. So this will also be obtained by rotating a particular angle and translating it. All these will, if you are traveling in this, in the unit speed, or traveling in this, in the unit speed, or traveling in this, you feel no difference at all, because in the same way you keep moving left and right in all of them. Because they all have the same signed curvature. So they all, it's something like one wire, you can say, solid wire. You bend it according to the data given by Ks. How you should bend left or right using Ks. Plane curve, you have to make it a plane. You can't bend it outside the plane. On the plane you keep it. Now what we are saying is that, so that determines the curve whose signed curvature is the given function Ks. Any other curve will be just moving this around, rotating it and translating. Any other curve that you get will be the same string, you move like this, like this, like this. That's the theorem that we are seeing.